Hello everyone. In this video, we will try to understand the traveling salesman's problem and its solution using dynamic programming. So to begin with, what is traveling salesman's problem? And then we will try to understand the solution. So in this problem, the idea is to find out a cycle in a given graph by visiting all the vertices of the graph once and again coming back to the source vertex. So it's a kind of basically it's a kind of circular linked list which will be starting with a source vertex and it will visit all the vertices of the graph and it will again end back to the source vertex. So if there are n vertices in the graph, then there will be n plus 1 vertices in the traveling salesman's problem solution because we are repeating the source vertex as destination. The main constraint is the vertex or an edge can be visited only once. And the motivation or the objective is to generate the cycle in the minimum cost. So since the optimization function is there, which is basically addressing to the minimum cost, this problem becomes a complex problem when it is basically solved for very large graph because not only you are required to derive the cycle from source to source, but also this cycle should be of minimum cost. So there is a selection with some constraint. So whenever this happens, any given problem which has large input will gets converted into complex problem and maybe can be categorized in the non-polynomial or non-deterministic polynomial time algorithms. So this particular problem is basically solved for complete graph. So when you represent the complete graph in the form of a matrix and which is also directed, then the diagonal elements of this matrix will be 0 and this lower triangular part and this upper triangular part will have non-zero and positive entries, and maybe they may be distinct also, so they may not have similar value, or we may say that a of I comma j will not be same as a of j comma I, so that the distance to travel from a vertex in a directed graph will not be same if it is from the destination back to source. So this is just an may not be constraint always, but just an idea to make the problem little bit more complex. So I hope you understood the idea what is traveling salesman's problem in the very again in a brief. It is a cycle which is starting from a vertex and ending back to the same vertex. Let's move ahead to the formulation. So we have the so whenever we are trying to derive the cycle, we will define the vertex as source. So in our formula, we treat that source as I, and here this capital S represents the vertices which are present in the graph, but not the vertex which is selected as a source. So S represent the vertices other than I, and out of these vertices, one vertex will be used as next intermediate because suppose there is a graph of 4 nodes, then there will be a path in which there will be five different vertices. And if we take first vertex as source, then this vertex will be repeated at the starting of the path and at the ending of the path. So then the remaining vertices which are there in the graph, like 2, 3, 4, can be considered as vertex J, and this can be also considered as set S. Okay. So if I want to start from a vertex I and I want to travel to some next vertex, then I will have to pay some cost. This cost is treated as cost of traveling from vertex I to vertex J, that is C of I comma J. C represents the cost matrix. Now, once you have decided that you started from I and you are landing to J, then your next path or next component of the path will continue from J and will try to use all remaining vertices of S other than J. That is S minus J. So this S minus J is nothing but if S is 2, 3, 4, and I have picked 3 as J, then S minus J will remain as 2 and 4. So then I will have to operate the remaining components, and then after operating on remaining components, the final minimum cost path will be derived. So if I start with vertex 1, then I will have the capital S as 2, 3, 4. And if I travel from 1 to 3, then I will be having remaining vertices as 2 and 4. So this formula will be recursively executed, and this execution will end when all these three different possible locations in the path are operated with this formula. So let us see how this is actually implemented on a matrix. If I go ahead and I take a 4 by 4 graph, then this 4 by 4 graph has four vertices, that is 1, 2, 3, 4. And there are these four vertices are connected with each other in the form of a complete graph. So diagonal elements are 0. So if I say this, I am taking 1 to 2, cost is 10. Okay. And 2 to 1, cost is 5. So my graph will briefly look like 1 to 2, cost is 10, and 2 to 1, cost is 5. And in this way, I will have remaining vertices connected. So if I try to draw what is the distance from 1 to 3, it is 15, and 3 to 1, it is what? 6. So this is the brief path which has 1 and 1 as source and destination. So we call these three locations as intermediate. And in traveling salesman's problem, the intermediate locations will be initially treated as so there is one intermediate here from this to this. If I stand here, then there will be two intermediates from this location to this location. And if I stand here, then there will be three intermediates. Okay. So in order to find out the optimal path, you will have to operate with each and every intermediate. And then once you operate with each and every intermediate, you can make the decision. So dynamic programming approach will not allow you to make decision till all the intermediates are resolved. So for example, if I want to travel to destination 1 with one possible intermediate, then the different values of this intermediates will be 2, 3, and 4. Okay. And since I am using one of them, then probably once I say I am using one of them, then I will have to find out what is the cost to travel from that particular selection to my destination. So suppose I select 2, then I will have to take 2 to 1. Suppose I select 3, then I'll have to take 3 to 1. And suppose I select 4, then I'll have to take 4 to 1. So my set S will not have anything if I use that 2 as the intermediate, or if I use 3 as intermediate, or if I use 4 as intermediate. So my formula will look like g of 2 comma 5, which will be treated as cost of 21. Why this 5? Because if I am using this location and I am traveling here, then in this case there is a direct path from either 2, either 3 or 4. So there is no intermediate here in between this vertex 2 and 1. But if I say this location, then there is one intermediate. And if I say this location, then there are two intermediates. So in this way, the formula becomes complex when I move backward and I have more number of intermediates. So for example, if I use 3, then I will be just having cost of 31. And if I use 4, then I will be having just cost of 41. So my formula with no intermediate will look like this. So if I say no intermediate means I am standing here and I want to travel to 1. So there is a direct path and there is no intermediate. Hence I can write 2, 3, 4, and I can take this as my uh, final distances from the matrix. So this 5, 6, 8 is coming from the matrix. Now the formula becomes more complex if I am using one intermediate. So for example, if I have the path like this, okay, and I'm writing one here and I'm writing one here, and I am standing at this location. So then I will have to travel here and then here. So this becomes my intermediate one. Now if I'm taking available vertices as 2, 3, 4, and I'm writing 2 here, then the possible intermediates will be what? Either 3 or 4. Similarly, if I am writing at asterisk 3, okay, this asterisk, if I am writing 3, then the possible intermediate will be 2 and 4, and they will be allowing me to travel to 1. And if I am writing at asterisk 4, then the possible intermediates will be 2 and 3, and then allowing me to travel at 1. So if I try to make it more proper, and if I write again, this is 1, this 1, and I don't know what I should write here, but if I am writing 2 here, then I cannot write 2 because vertex cannot be repeated. So if I'm writing 2, the possible options to write at this point is either 3 or 4. So look at what we have done here. We have already solved 3 and 4, and we know that from 3 to 1 and from 4 to 1, what is the distance. So similarly, if I want to write what at this location, not 2 but 3, then I will have to use 2 and 4, and already I have solved that in the previous step. So if I am starting from 2 using 3, I am traveling to 1, the formula will be traveling from 2 to 3 and 3 to 1. So 3 to 1 is already solved. And if you look at the matrix, 2 to 3 is 9, okay, and 3 to 1 is 6. So these two will contribute total value to 15. Similarly, if I want to travel from 2, then 4, and then 1, then I can use what? 2 to 4, that is 10, and 4 to 1, that is 8. So this will generate value 18. So just to, I'll skip this, but I'll just explain this one again. So if I am at 1, and at this point I'm writing 4. So using this blank, if I'm traveling to 1, then this blank can be either 2 or 3. So 4 to 2, 2 to 1, or 4 to 3, and 3 to 1. And this is the y. Further going ahead, and if I make this more complex, then I have the path, okay, 1, 1, and now I am standing here and I can use these two as intermediates. Okay. So if I am using these two as intermediate, my choice becomes broader. So if I'm writing 2 here, then this 2 can be either combination of 3, 4. Okay. So my path will be 2 to 3 to 4 to 1, or 2 to 4 to 3 to 1. And it will be written as g of 2 comma 3 4, okay, which will be equal to minimum of what? I will take first option as 23 and I will take second option as 24. And then from 3, okay, using 4, I will reach to 1, or from 4, using 3, I will reach to 1. Okay, so it is 4 comma 3 to 1, or 3 comma 4 to 1. So where it is already solved, this component is already solved here. Look at this, 3 to 4 and 4 to 1. Okay, and where this is solved, 4 to 3 and 3 to 1. So 4 to 3, what? Here, 4 to 3 and 3 to 1. So in this way, if I'm not writing 2, right, and if I'm writing 3 here, then my possible choice will be 2, 4. And similarly, I can also write 4 and possible choice will be 2, 3. So if I take this one, then what? G of 4 and writing what? 2, 3 as intermediate. So either travel from 4 to 2 or either travel from 4 to 3 and then continue from 2 but make use of 3. Okay, and continue from 3 but make use of 2, and this way you can continue. In this way you will get the problem almost solved from the stage 2 to stage destination, and then this partial results can be used to solve the problem from stage 1 using all remaining vertices as possible intermediate. So let me show you this one. So if I'm writing 1, then my possible option to write here are 2, 3, 4, and then again I'm traveling to 1. So my first choice can be 2, and since my first choice is 2, I will be making choice between 3 and 4. Okay, so my 3 and 4 choice is already solved here. If my next choice is 3, I will be making choice between 2 and 4, which is already solved here. And if my next choice is 4, then my possible choices can be 2 and 3, which is also solved here. And out of this all solutions, I have the minimum values derived. Okay, so no need to recompute. So if I'm taking this cost, how to calculate? So 1 to 2. What is the distance from 1 to 2? 10. And the distance 25 is added. Similarly, 15, 25 is added, and 30 and 23 is added. Okay, right? So what is the distance between 1 to 4 is 1 to 4 is 20. So we have just misprinted here. 1 to 4 here is 20. So 20 plus 23. Okay. Now, after all this, if I want to solve how to calculate the path, so what I will do is I will draw 5 blanks. Okay. This is my vertex 1. This is my vertex 1. And I'll refer the last step. Out of the last step, my minimum value is 35, which is coming from this option. So this option represents traveling from vertex 1 to vertex 2. Hence, I will write 2 here. Now, what should be referred? This component should be referred. So this component should be referred. And in this component, I am getting 25. So which particular value is giving me 25 needs to be checked. Okay. So I'm getting 25 from 4. Hence, I will write 4 here. And then I will try to get to 3. And from 3, I will reach to 1. So in this way, you can always verify your answer as well as you can also verify the path. And once you refer the matrix and find the values in the matrix, you will be able to determine whether your answer is correct or not. This problem has many applications in the current machine learning and artificial intelligence scenario, and you can always check what are the different applications of traveling salesman's problem. I hope this video help you or will be useful to you to understand the TSP problem as well as finding the solution for this problem. Thank you.